Investigating Resistive Forces Lab, Group 11, Section 4. In this investigation, we are trying to understand how viscosity affects the increase of resistive forces. Viscosity is a measure of a fluid's resistance to flow and displacement. All tested fluids have different viscosities, and we used a slow-motion camera and a ball bearing to track position and velocity. Then we calculated the time necessary to determine what the rate of force resistance over time would be to compare with viscosity. Resistance force is an internal force that acts in the opposite direction of motion. In a fluid, resistive force will increase constantly until it is the same magnitude as the force applied. When this happens, F net is zero and the object is traveling at a constant velocity, called terminal velocity. This increase happens over a time period. This time period will be different based on the viscosity of the fluid. Viscosity is a measure of a fluid's resistance to flow and displacement. Our group wants to prove a relationship between the viscosity of the liquid and the rate that the resistive force, Fr, increases in a fluid. We believe the more viscous a solution, the larger the rate of change will be, with each subsequent trial reaching terminal velocity faster. A more viscous solution should resist the force gravity faster and create a smaller time until terminal velocity is reached. Using what we know about the rate equation delta y over delta x, and the fact that at the start of the drop Fr will equal 0, we can write a formula for rate of Fr as this. In order to find delta T, 5 different fluids were used: water, isopropyl alcohol, vegetable oil, dish soap, and corn syrup. Each of these fluids had a different viscosity. A small ball bearing of constant mass was dropped into a graduated cylinder of each fluid. Using the program tracker, the position and velocity of the objects were calculated over time and their graphs made. Looking at the velocity time graph for each bead, we can see where terminal velocity is reached by finding where the graph stops decreasing and stays constant. Subtracting the time the bead starts falling from the time the terminal velocity occurs, you can find the delta T for the trial. Using this method, we were able to find the delta T values for each fluid, tracking the footage twice to avoid error. The massed beads were 0.00835 kilograms. By multiplying by 9.8 meters per second squared and dividing this number by the delta T value of each track, we get the rate of resistive force over time. The first of our 2 tracks is charted here. The relationship between viscosity and rate of Fr is not as clear as we would have liked. R squared of the best fit line is only 0.4, and the values of the rates are not always increasing with viscosity. Despite this, there is still a positive correlation of 0.8577 newtons per second squared. The data collected from our second track, however, is more in line with our predictions. The R squared value for this line of best fit is 0.93, which is fairly high. The rate generally increases with viscosity, as predicted, except for alcohol, which seems to be an outlier. There are clear problems with both tracks, which will be discussed in the errors section. Despite this, we still get a positive slope for both tracks. This slope ranges from 0.86 newtons per second squared to 0.106 newtons per second squared, with an average of 0.958 newtons per second squared. This is almost a one-to-one relationship between the rate of change and the viscosity, showing a clear positive relationship. There are several things in this lab that could have caused error. While we have 2 different people tracking the video of each system, we only recorded 1 video per fluid. Any bumps in the bead's descent, such as a large air bubble moving upward, would affect every track for that fluid. Something like this could have happened in our water trial, as both tracks have a delta T smaller than the more viscous alcohol, which seems erroneous. More trials would have helped clarify this. Another error comes from the device we used to record. The frame rate of the iPhone was too low to detect the very similar delta T values for many of these fluids. As a result, we only have 3 values of delta T between 10 trials, the times for 1 to 3 frames of video. With a higher frame rate camera, we would get more varied delta T values. Our model also assumed the bead would have an initial velocity of 0 meters per second, but due to the gap between the fluid and the top of the graduated cylinder, the beads hit the fluid with a varying initial velocity. Using Tracker, we can see some of these starting velocities. A starting velocity might change the time it takes to reach constant velocity, skewing our results. Ultimately, our goal was to determine if there was correlation between the rate of force resistance and viscosity. And despite the errors that we came across, we were still able to provide evidence for a positive relation between those values. From these calculations, we can safely assume that the rate of change in viscosity do have a ratio of 1 to 1, meaning force, resistance, and viscosity do correlate positively with each other.